Okay, I had a few disasters while I was trying to do this live, so I thought I'll just run through it quickly. Not live, and we'll see how it goes. So this is all about structures to store data. Quite a lot to be covered in here. There's linked lists, graphs, directed and undirected, stacks, queues, which are stack is a depth first search and a queue is a breadth first search of a tree or a graph. Trees, in particular the binary search tree, and hash tables. Now they don't quite go in that order, but stick with it. Fingers crossed you'll get something from it. I will change my pen colour now because I think red is more interesting. There we go. Okay, so this is all about arrays. Now if you have a look at this bit here, this represents an array of memory. This represents your memory. From here to here is the array that you define. So what you're doing here, you are saying in new array of 5, and that reserves 1, 2, 3, 4, 5 spaces. Nice and easy, and that's good. There's nothing wrong with that. The problem with arrays, and what you'll need for your exam, is that they are inflexible. So you have 5 spaces in this particular array, and if you then realise that you need to store more data, let's say you're setting up a company, and your company initially has 5 staff, so you create this array of 5 for storing details of your staff, and then your company starts to grow. Then what you need to do is you need to create a new array which is much larger, so it's not flexible. And let's take that argument in reverse. If you were to create a company and you think it might get very, very big, so you create an array of 5,000, then that's great. You won't run out of space in your array. But of course what you've done, you've reserved 5,000 slots in your memory, which is going to make your program very inefficient. So they're inflexible, but they are very, very good. You know, they're well used, and they're nice if you know how big your data is going to be, and that data is not going to change. Okay, so this next slide basically talks through what I've just done. The fact that in here we've got some different colour again. In here we've got some wasted space, and in here we're not using enough of the space, so our program's inefficient. Did I mean that? Yeah, both of them show inefficiencies because both of them are showing that the array is not being used fully. You can read that. I'll take that off for you. You can have a read. Pause it if you want. Okay, so an answer to arrays are linked lists. And linked lists are a dynamic storage method. Remember that word, dynamic. And the way they work is you store your data. Let's find a colour that's going to work on here. You store your data here, and then you create a pointer. And initially, when your linked list doesn't contain any other data, that pointer will equal 0. But that will change as soon as you start to add some data, and that pointer will become a pointer to your next element. And then you'll put more data in here, another pointer to your next element, more data here, another pointer to your next element, and that can go on forever. So you're only creating the storage as and when you need it. So you've got over that problem of flexibility in the array. The problem that you still have is that now what you've got is you've got 2 bits of data where before you only had 1. You've got the data plus you've got the pointer, so you're using double the amount of space. There is another problem with them, and that is if you want to get access to this piece of data here, the only way you can find it is by going in here, looking for it, then moving across to here, looking for it, then moving across to here, looking for it, and then moving across to there. So there are some disadvantages with it. And if you imagine this is a very, very long list, then that could take a long time to do. So advantages and disadvantages with both. This video is quite long, but it's useful. I would suggest that you watch it, and the way to watch it, unfortunately, is to either type in that big long address, should have used a shorter one, or to get the PowerPoint itself rather than this video and just click through and have a look at it. But it's generally quite useful, probably a bit more detailed than you'll need for your exam. Okay, you can code a linked list, although I wouldn't recommend doing it in C#. The reason why you shouldn't do it in C# is because C# doesn't cope with them very well. It doesn't like pointers, and what C# does, it uses something called a list, using this notation. And a list is different to what we're covering for the spec of this A-level, but a list will grow dynamically, and is a good thing to use. But if you want, you can use a thing called a struct, which is the C# way of creating linked lists. But in reality, I wouldn't worry about implementation of linked lists for the purposes of the exams. You really just need to know the advantages and disadvantages. Okay, so here's an exam question. Do feel free to pause it and give it a go. And on the next slide, I will I won't give you the answer. You can come to me if you want the answer. It came from this book here, so yeah, I'm sure you'll be fine with that. We did it in class anyway. Okay, so on to graphs. Now, graphs are a way of storing quite complex data, and they are linked together in a variety of ways. And what you need to do is you need to understand that the dots are called vertices, and the edges, or the lines connecting them, are called edges. So we have a vertex there, an edge there, and another vertex there. They're the terms you need. Here we got a graph is a complex data structure, which we may need to store in a computer program. They're often used to represent real-world scenarios like a map or group of things that have complex relationships. There are two ways to store a graph. You can use an array, which gives you an adjacency matrix table. You'll see that in the next few slides. Badly drawn table there. Or you can use a linked list, which gives you an adjacency list, which has sort of arrows like this, and that shows you what is next to each item, what they're connected to, what each vertex is connected to. Okay, so that's an adjacency list. There. If I ever stop doing this, I can get a career in art. There we go. Okay, so the degree of the vertex, I don't think you'll need this for the exam, but it's fun to know. So it's the number of edges touching a vertex. So in this case here, this vertex has a degree of 3. 1, 2, 3, or degree 3. This one here, you can calculate that, I'm sure, has a degree 4. And this one here, nothing's connected to it. It's like a station with no trains. This is degree 0, and that is allowed. You can create vertexes that aren't connected to anything. Okay, so the graph itself the shape of it doesn't matter. These two have the same number of vertexes. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. They are the same. If you want, you could use that game if you want to sketch out some graphs, planarity.net, but you don't really have to. Paths. A path is a route around the graph. This path here covers 3 edges, and that's a length. So that path has a length of 3. You can't repeat an edge, so you can't follow this path and then decide you're going to go back. So just one thing you should be aware of. Although I don't think for the exam we go quite that much into depth, so you can probably not worry too much about paths. Okay, 3 graphs here, all separate, absolutely fine. We understand basically what they are. However, these could be the same graph. It could be the same graph consisting of 20 vertices. That's fine. It would just be known as a disconnected graph. So, one graph, if this is one graph on one piece of paper, you might represent, what might you represent? You might represent friends on Facebook. So this is one group of friends, and this is another much bigger group of friends with a more interesting shape, and this is another one here. But none of these friends know anyone here, and they don't know anyone there, and vice versa. So that's a disconnected graph. Okay, so loops and directed edges. If a vertex has a link to itself, that would be called a loop. And this particular vertex here now has degree 5. 1, 2, 3, 4, 5. And some edges, which we haven't seen yet, are directed. So this one here, you can only travel in that direction. You can't go back again. You can also add weight to your edges. So these are cities, and the numbers are the weight of the edge. And in this case, these numbers represent the miles. So 337 miles from San Francisco to Los Angeles. I'd imagine that would be shorter. Anyway, America's a big place, so 337 miles. So that's weights. Okay, here's I put an useful example. That should obviously be a useful example. So cross that out and pretend you never saw it. This uses directed edges. This is an unweighted directed graph, and in this case we can see the paper covers rock, rock covers scissors, and scissors cut paper. Nice and easy. Won't spend any more time on that. Okay, so how can it be useful in computing? Well, I've mentioned Facebook already, so here's a Facebook graph. I took this from the site here, and this shows who's friends with who. Now this is an undirected graph, and it's also a disconnected graph, because this is all Facebook, all FB, but this group of friends here are not friends with this group here. And also we have to have we can't have directed friendships, because if we did that, then we could make AJ friends with Sarah, and Sarah wouldn't want to be friends with AJ, which would be a bit weird. So these are undirected relationships. Okay, so another representation you might want to use are a website. You might show how website pages are linked. So I've looked at this a few times. I can't figure out what the home page is. The home page should be connected to pretty much everything, and it isn't here. For example, page C, I'm not quite sure where you'd come from. to get into page C. It's a bit weird because it only links to page A. Anyway, that said, you can see the direction of the links, which helps you to understand it. Again, unweighted because there are no numbers against it. If you were to put numbers against it, by the way, you might think of those as hit. You know, the number of people who travelled from C to A, that would be the hit rate that followed that link. Okay, so storing the data in the array in an adjacency matrix. The adjacency matrix is this, and it forms an array. Now these are quite easy to read. If you follow across this direction, A has no link to itself. It has a link of 3 to B. So that's, if I use sort of yellow, which is quite close to the colour. Now we know that has an arrowhead because it's a link to B. We're not going to follow it back the other way. So when you're doing an adjacency matrix, initially create arrows, and then if it turns out they're all duplicated, then you can take the arrowheads off. But if you have a look in this graph, this 3 here on A to B does not match up with this one here, so it's not symmetrical. So therefore these are directed. This is a directed graph. I'll just follow through A again. So there's no link to C, no link to D, and there's a link of 1 to E. So it's got a weight of 1. I didn't write the weight of 3 on that one. Okay, I'm going to skip through B, I'm going to skip through C, and I'm going to skip through D, but I'm going to come back to E, and I'll draw this one in. So E has a link to A with a weight of 1. Aha. Now, this is a line in this direction here, and then there's a line in that direction, and they both have a weight of 1. So you can merge those two, and that can become an undirected link, edge, because the weight's the same. If we go across to this one, if we go across to this one, a link between E and D, okay, well there's a link there of 3. Now we've already drawn a link from D to E with a weight of 1. This link going back has a weight of 3. So therefore, that must be a separate line. We can't have the same line because it's a different weight. You might think of this as a bus route. The bus route in one direction only takes a mile to get from D to E. That might be because the one-way streets run in its favour. Coming back, he has to go all around the houses, and it takes 3 miles. So it's a different, distinct route. Okay, we can also store it in a linked list. Now, if you have a look, there's far less data in here than there was in the adjacency matrix, because there's no need to store those zeros. So here we've got a link between A and C, and we can draw that link in. Again, we use an arrow because we're not sure what's going to happen. I won't do that one. I'll come to C. C's got a link to A. Now this is unweighted because there's no numbers, and we can see that that's a perfectly acceptable link. So what we could do, we could remove that arrowhead, but it's a good idea to leave it in place until you've done everything. As you go through this, eventually you end up with links in both directions. Because they're unweighted, it's acceptable just to put the arrowhead straight on there. But what I would recommend is that you stick arrowheads on, and then at the end, when you're doing the write-up, say this is an undirected graph. Okay. Storage efficiency. So let's have a look at an adjacency matrix here. M and this one here. You know what? I've forgotten the name of it. Anyway, link this here. Link this. So if we have a look here, this 0 to 1 is replicated here, 1 to 0. These two here are also replicated here. And if we were to draw down this line, we'd see that they're all the same on either side. This side basically is the same as this side. We'll take all that away. So if we're going to calculate efficiency, we only need to tot up the numbers on one side of this line. So 1, 2, 3, 4, 5, 6, 7, 8. 10 by 10 gives you 100. So there's only 8 being used out of a possible 100, which gives us 8% efficiency. Now, you won't need the efficiency for the exam, but what you will need to be able to do is you will need to be able to say that this is almost always more efficient. The linked list way of storing things is almost always more efficient than the array for graphs, because you don't need to store null values in the linked list. Okay, so adjacency list versus adjacency matrix. There's a nice video that you can look at there if you want to see a comparison. Remember, you have to go to the PowerPoint if you want to look at that. Okay, so algorithms to help you find your data. Algorithms are structured methods of searching or traversing a data structure, such as a graph, or a linked list, or a tree. A graph is one method of searching. It works on last in, first out. And when you use a stack, you add, or you push data onto the stack, and you pop data from the stack. So if you consider a vertical tube and you push numbers or blocks into the tube, and then you pop those numbers out again. And if you were to push the letter A in first, and then 3, and then 12, and then B, and then 31, the first one you get out is 31. So it's last in, first out. A queue, well, you should know how a queue works. S gets into the post office first, then 31 gets in there, and then C, and then A, and then 3, and then 12, and then B, and then 31 comes along at the end. S will be served first because they join the queue first. So this is a FIFO method of storing data, and it means first in, first out. Okay, you can either use a stack, which is a depth first traversal. Remember the shape of the stack, it was that way, so it's depth first. Or you can use a queue. Remember the queue is this shape, so that is a breadth first traversal. Okay, I would suggest you look at that video, and I would suggest you have a short break. Right then, trees. Trees are a restricted form of graph. They have a parent-child relationship, and they don't contain any cycles. Here's an example of a cycle, just there. It's a recursive relationship, a cycle. That doesn't happen in trees. Trees just exist. Binary trees can have 2 children. I'm just reading on here. A tree is a restricted form of graph. Trees have a direction, parent-child relationships, and don't contain any cycles, with restriction that a child can have only one parent. Okay, so a child can only have one parent. In a binary tree, you can only have up to 2 children. So you can have 0, 1, or 2 children. I'll go through those a little bit later. It says finally trees there, but I will come back to trees. Okay, and here's a little puzzle that you might want to have a go at. Do come to me if you want to get the answers. Okay, so hash tables. Hash tables are a halfway house between linked lists and arrays. So we've got arrays which are fixed, and we've got linked lists which are dynamic. The problem with linked lists is that if we're after this number here, number 82, the only way we can get to it is to start at the start and work our way through all of the elements until we find it. And if this is a particularly long data set, and that becomes a problem. Let's say you're searching through, I keep using the same example, but DNA. Let's say you're searching through DNA and you want to find a particular strand of something DNA related. Let's say you're trying to match up a burglar with a crime, then that could take a very, very long time using a linked list. So hash tables give us a solution to it. And the way the hash table works is that there are two ways to look at this. I'm going to use the C# way. The video, the lady in the video, talks about the another way where the data is used as a key. Don't get too hung up on that, just understand the basics of how they work, and this is the basic principle of how they work. You give it the data and in some cases a key. In C# you give it a key as well. You feed that into a hashing algorithm here, and that hashing algorithm is a computer code which determines where physically it wants to store it, and then it stores it. Now you can visualize this as an array type table with positions, and if you put some data in here, let's say we're going to give it the number 101, and we're going to store the word, let's be politically correct, we're going to put a rabbi in. Okay, so we feed that into the hashing algorithm. The hashing algorithm does something magical, and it decides to store our rabbi here. Now, you might think, oh, well, that corresponds to an array, but it doesn't. This hashing algorithm has determined where to store it physically. You can give it the key 101, but it doesn't necessarily correspond to a traditional array like that. It's dynamic storage. So it's good really just to be aware of the fact that you can feed this data in and you can search for it. Now the advantage this gives you over an array is that this isn't static, this is dynamic, and also you have the ability to find data a lot quicker because you don't have to search through the entire table like you do with a linked list, because you've got that key, you've got a position which roughly corresponds to where the data is. Okay, now these videos are very, very good. I would suggest you watch them. Try and bear in mind the word collision clustering and separate chaining as you do watch them. If you choose not to, then what you need to remember is essentially how a hash table works. Pretty much it. There are halfway house between arrays and linked lists, and they work faster than linked lists, but they are dynamic storage. Okay, these were questions asked in class. Feel free to answer them again, and do have a look at the books that you've got, the student books, because that will answer all of those as well. Also in here talks about big O notation, which is going to be useful to understand for most of the videos because they refer to constant time, and ON, which is sort of unspecified time. Some information on hashing, do feel free to read it. I won't read through it, press pause if you wish. And implementation. Okay, so here's a way that you can implement a hash table in C#. Not vital for the exam, but quite fun to do. I think this is the final section, which is nice, slide 35 of 45. This is binary trees. Covered this briefly a few slides ago, and I'm going to cover it again now. So I've got a few terms for you. First of all, this is the left child, this is a right child. They are children of C. C is also the right child of A. This is a subtree, this is the right subtree, this is a left subtree. Okay, let's move on. What bits are important here? Okay, so nodes with no children are called leaves. So the leaf, D, E and F are all leaves. And nodes with the same parent, like E and F here, are siblings. Isn't that nice? A few more terms. The depth of a node is the number of edges from the root to the node. So this is the root here, top one, and the number of edges to C is 1. There's only 1 here, so the depth of C is 1. The number of edges to get to E is 2, so the depth of E is 2. The height of a node is the number of edges from the node to the deepest leaf. So working in reverse, essentially, C is 1 high because that's the deepest leaf there, F, and A is 2 high. It has a height of 2 because it has to go through 2 to get to the deepest leaf. The height of a tree is the height of the root, so that's 1, 2. And a full binary tree is a binary tree in which each node has exactly 0 or 2 children. So this is not a full binary tree. It is a binary tree, but not a full binary tree. And hopefully you can have a look at that and figure out why. Okay, ho ho ho, almost Christmas. Well, it isn't for me. Traversing a tree structure means walking around the structure so that each node in the tree is visited once. That's what that word means, traversal. Please understand what traversal means. It is very likely to be in your exam. Father Christmas needs to traverse every tree in order to deliver all the presents. So I thought it was an appropriate image for you. It looks a bit sort of Stalinist, doesn't he? A bit like a sort of dictator of some sort. Anyway, I'm sure he isn't. Anyway, pre-order traversals. This is one way of doing it. Now these aren't particularly clear to me as I first look at them, but generally you lot as students seem to get it pretty quick. So, pre-order traversal, we visit the root first, we traverse the left subtree, so remember the subtree is that, and then we traverse the right subtree. So, just looking at this tiny diagram here, pre-order, we start at the root here, we traverse the left subtree, and then we traverse the right subtree. So that gives us D, A, E. Here we start at the root, traverse the left, then we traverse the right, and we can go left again, and then we're done with the left subtree entirely, and we can go up to the right subtree. And again, we prefer the left, so we go to the left first, no other lefts to do, go to the right, left again, etc. So you can probably figure out your way around using pre-order. In order, we go to the left subtree first. Now, there's some arguments about which is the first on this one. Then we visit the root, and then we visit the right subtree. So we go to the left subtree in order. So if we have a look at this diagram, that's actually wrong, because that should start off 2, 4, 5, that would be our left subtree, then visit the root, and then visit the right subtree. So ignore that diagram, that's a mistake. But if we have a look on the one that isn't a mistake, here, we go to the left, A, then we visit the root, D, and then we go to the right subtree, E. So A, D, E. Moving on. Post order. We go to the left subtree in post order, we traverse the right subtree, and then we visit the root last. So left first of all. This is the furthest left point, that's why we start here. Go down, back up, across into the right subtree, and again in order. So we're just following that line around, and then we eventually end up at A. Easier to look at this, which gives us post order. We start on the left, which is A, then we go to E, and then we go to D, which gives us AD. Okay, here's a quiz here. Now I've got answers popping up on my screen. I'm not sure if you will. So I'll give you them real quick, but I'd suggest you pause it, have a go, and then I'll come back to it. So pre-order. D, B, A, C, F, E, G. In order. A, B, C, D, E, F, G. Post order. A, C, B, E, G, F, D. Hopefully you got all that right. Okay, this is the same tree but using different notations, so you should be able to follow the same route around. Pre-order. Plus, multiply, AC over EG. In order. A multiplied by C plus E over G. Post order. AC multiplied by EG divide plus. The order of evaluation is for in order is A multiplied by C plus E divided by G. And post order is actually reverse Polish form. Now if you want to look that up you can. So it's AC multiplied by EG divided plus, and reverse Polish form will give you a slightly different output to in order. So sometimes you can use it for producing different formulas, maybe different equations. The other thing you want to be aware of is you've got two quite complex data sets. You want to make sure that you follow the same path, otherwise you might get a little bit confused. Here was the homework that I set. Okay, so Brutus, Bavarian Prince, and what I asked you to do was to think of a data storage method that Brutus could use. Remember, we've got linked lists, we've got arrays, we've got hash tables, graphs, etc. And I want you to think of which is the best and why. A bit more there. And these are the reasons why he wanted to do it. And what I suggest you do is open this up and just have a quick read through it, because hopefully it's written in quite a light-hearted, easy to follow way. Anyway, I'm going to stop talking now, and fingers crossed this will be my first successful video. Hurrah! Okay, good luck.